All right, in this video I'm going to be talking about systems of nonlinear equations, which is a topic that seems to be not overrepresented, but represented on pretty much all of the CLEP practice materials. Okay, when I took the CLEP exam, I saw some nonlinear systems on there. And we've already studied systems of equations at least one point in this year. When we studied linear functions, we solved systems of linear equations, which is basically there were no exponents anymore. And so what we did was, for this one on the left, this one was kind of primed for substitution because we had this x equals and we could just plug in on x. And so I remember we used substitution for this one. Whereas the one on the right, I'm seeing this negative 3y and positive 3y, that's primed for elimination. So we use substitution and elimination to solve systems of linear equations at the beginning of the year. And now that we've got systems of nonlinear equations, we're going to solve those using substitution and elimination, just the same. Now, I will say that when it comes down to it, you are probably going to be doing more substituting than eliminating on these nonlinear systems, but it's the same principles at play. And before I start actually solving some of these problems, I'll just say that, or talked about, what is a solution to a system of equations? And so remember that it's values of x and y that make both equations true. And remember that the graph of a function, is the set of all pairs of x and y that make the equation y equals f of x true. So if I've got kind of two equations, and especially if they're not linear, like they could be curved, well then these solutions that make both equations true, these xy coordinates that make both equations true, are going to be the intersections of the graphs. For the most part, it's going to be very algebraic. We're just going to be given two equations and we're going to reduce them down and we're going to get xy coordinates, or a few of them. But it's good to keep in mind what we're doing here. We're looking for places where graphs run into each other. Okay, and the first example I've got for you is a question that asks, how many solutions does this system have? Now, on your notes packet, it probably doesn't say that. It just has this system. But that's something that I'm going to ask on the quiz and maybe even on the test, like, not what are the solutions, but just how many are there? And so what that requires is that just means you got to, get it down to kind of one variable, and it's probably going to be quadratic, and you'll use the quadratic formula to determine the number of solutions, but you could just stop once you figure out how many there are. So this one is, we're going to need to use substitution. Unless it's just looking like it's primed for elimination, you're going to want to use substitution. Okay, this one, if you tried to eliminate, there's really nothing that could cancel off besides the 5s. And then you would still end up with y squared, x, and x squared. It's really going to be difficult to separate all that out. So what I'm going to say is I'm going to use substitution. And specifically, I'm going to substitute on y. And the reason for that is that, you could solve for x on the first equation, but you'd have to add y and then divide everything by 3. And that's kind of annoying. I think it would be a lot easier to say, okay, well, this thing is going to give me y. If I subtract y, or add y and subtract 5 from both sides of the first equation, I'll get y equals 3x minus 5. And that's going to be the way to go. Okay, so I can go ahead and wherever I see y in the other equation, I'm going to substitute 3x minus 5. Okay, so what I have now is x squared plus 3x minus 5 squared is equal to 5. And, okay, I'm doing this right off the bat because I just want to remind you that 3x minus 5 squared is not 9x minus 25 or 9x plus 25. Remember, we actually have to square this thing. So what I'm going to do is I'm going to actually multiply this out. And so this is going to be x squared plus first outside, inside, last. And then I'm going to kind of, combine like terms, clean it up, set it equal to 0. I'm going to get 10x squareds, negative 30 x's, and positive 20 equal to 0. Now this is the type of equation that I can analyze and determine the number of solutions. yes, it is definitely factorable, and you could take it all the way. And if you feel like that's something you need to practice at home, that's something you could kind of sweep up behind me and do. But what I'm going to do instead is I'm going to just say, well, I know that if I've got a second degree polynomial and it's equal to 0, x equals negative b plus or minus the square root of b squared, 30 squared is 900, or negative 30 squared is 900, minus 4 times 10 times 20. Okay, 4 times 10 is 40. 40 times 20 is 800. All over 2a. And now I'm taking the square root of 100, and that's 10. So I'm going to take 30 and I'm going to add 10 and subtract 10. So that means I've got two different solutions. Okay, now there is a chance if you had like a parabola and a circle that there could be more, but if there's a line, it's really limited to just two solutions. In general, your possibilities with parabola line are going to be, here's your parabola, there's a line, that's two solutions. Here's just one solution, and we would call that line tangent to the curve at that point. Yeah, I'm not sure what happened there. And then if the line sat like that, there would be no solution. So if I see that there's at least two solutions, I know there would be two solutions in this case. All right, now it's kind of time for us to actually solve some systems of nonlinear equations. Here I've got a third-degree polynomial and a first-degree polynomial, and it's where are they running into each other? Okay, you've got two options as far as I see it. You could use substitution on y, which is pretty much the most obvious thing to do. Okay, so if we're going to substitute on y, I'm going to say that, well, y is equal to y, so that means that x to the third plus 2 is equal to x plus 2. Now, I'm also going to point out that if you did elimination on this equation, because you could eliminate the y's, you could subtract the second equation from the first, so y minus y is 0 is equal to x to the third minus x. Can't really do anything with that, besides just say x to the third minus x, plus 2 minus 2, which is going to be 0. And notice that over here when I did substitution, if I just set this thing equal to 0, I get x to the third minus x equals 0. So it really doesn't matter whether you choose substitution or elimination. You're pretty much going to end up with the same thing. Now, there are plenty of them that elimination just is not the way to go, and you won't be able to get anything from it. Okay, so now you've got x to the third minus x equals 0, and I'm going to start solving on that. And I'm going to need a little room for this. So I'm going to start by factoring. So I factor out an x, and I'm left with x squared minus 1 equals 0. And I'm going to keep factoring, because x squared minus 1 is factorable. And so this is 3 things multiplied together to equal 0. And if 3 things multiply together to equal 0, that's going to be because one of them is 0. So either x is equal to 0, or x plus 1 is equal to 0. Now, x plus 1 would be equal to 0 when x was negative 1. Or maybe x minus 1 is equal to 0, and that would happen when x is positive 1. So for each of these, you have to go back and figure out what y is. Okay, so I'm going to maybe space this out a little bit. And then for each of these, I'm going to go back and find what the corresponding y is. Now you've got both of these options, and the numbers that we have right now aren't that complicated, so it really wouldn't matter. But in general, when you're going back to find the value of the other variable, you want to choose the simpler looking of the two equations. And if I could choose between just adding 2 to a number and cubing a number and then adding 2 to it, I'm going to choose just adding 2 every time because it's, less stuff to do. So what I'm going to do is we're going to say, well, if x is 0, y is equal to 0 plus 2, which is 2. And so my solution is 0, 2. Okay, that's the coordinates of the intersection. At x equals negative 1, y equals negative 1 plus 2, which is positive 1. So x is negative 1 and y is 1. And at x equals 1, y equals 1 plus 2, which is 3. So I have 1, 3. is the third solution. These are, you know, your answers or your solutions. They're the intersection points, the places where the graphs run into each other. Okay, here we've got one where it's definitely not an elimination problem, I don't think. It doesn't look like it. And so it's going to be a substitution. And I have to decide, should I substitute on x or should I substitute on y? Okay. If I were to substitute on x, I would have x equals y plus 9. I'll just do this kind of maybe in gray. But then when I would go into wherever x is to substitute it, I would have to first, you know, square y plus 9, and then I would have to distribute a 4. And that's probably not going to be the easiest way to go. So rather than doing that, what I'm going to do is I'm going to substitute on y. And there's only one place I would have to substitute, and it's going to be, you know, something like x minus 9, and that'll be much easier to work with. Rather than squaring a binomial, you know, distributing in a 4, collecting like terms, all that stuff, that's a whole lot more work than we need to do. If we take a second at the beginning, stop, and think which variable should I substitute on. So I'm going to substitute on y. Okay, solving for y, I'm going to add y to both sides and subtract 9. So y is equal to x minus 9. So then, wherever I see y, I'm going to replace it with x minus 9. So x minus 9 is equal to x squared, 4x, and 5. Now all of a sudden, this is something that we definitely know how to solve. We're going to set this thing equal to 0. So I'm going to subtract an x, so that would become 3x. I'm going to add 9. Becomes 14. Oh, interesting. Well, I'm having trouble thinking of two numbers that multiply to 14 and add to 3. So, in the absence of being able to factor this thing, we're going to use the quadratic formula. So we know that x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Now, I can see, I'll be honest, I don't know what 4 times 14 is. I think it might be 56. Yeah, it's definitely going to be 56. But either way, it's going to be a lot bigger than 9. So this is asking me to take the square root of a negative number, which means I'm not going to have any real solutions, which means I'm not going to have any places where the graphs run into each other. Okay. So I can just go ahead and stop, since it's asking me to take the square root of a negative number, and I'm going to say that there are no intersections or no solutions. Okay, here's one that is very similar to one that I saw on the CLEP I took and that I have since seen on practice CLEP materials. Okay, the way it was shown when I took it was basically, here's a picture of the graphs of, and then they gave you the equations, and I'm not sure how much I'm allowed to say. It was very similar to these equations, but not these same numbers. And there was a parabola that kind of went through it, and then it had labeled this point A and B. It gave you the coordinates A and B. And it said, what is the value of, I can't remember if it asked for the value of A or the value of B. I think it asked for the value of B, because there's kind of a shortcut to this that I want to show you. Yeah, it definitely was asking for the value of B. But I think it would have been kind of a good question to ask for the value of A in terms of a multiple choice setting, because you could have the positive and the negative one, and, well, it's going to be the negative one because it's where x is negative. But I'll have more on that. So that is not what this system looks like. On this one, the parabola is actually going to reach all the way down and touch right there. I'll just tell you right now it's going to have 3 solutions. But I'll show you what the easy way to do this is. Okay. You could substitute on y. It looks like it really wants to be substituted on for y. But the play is to substitute on x squared. Okay, if you substitute on x squared, you're going to have x squared equals y plus 2. And then wherever you see x squared, you're going to replace that with y plus 2. So y plus 2 plus y squared equals 4. Otherwise, you'd have something that ended up being fourth degree, and you could solve it, but that's not the fast way. So I'm going to set it equal to 0. Y squared plus y minus 2 equals 0. Okay, and then you're going to say, okay, either y equals negative 2, that would be this point down here, or maybe y equals 1. All right, I kind of lost my place, forgot what I was saying, but I've got these two y values, and I'm going to try to find the x values that correspond to them. So I know that I don't have an equation for like x equals, but I do have this thing that I was using to substitute on x squared, so I'm going to use that equation. X squared equals y plus 2, so x squared equals negative 2 plus 2, meaning x squared equals 0, and that can only happen when x is 0. So the solution that I get when y is negative 2 is 0, negative 2. Now this shouldn't be surprising, because that's what I was saying earlier, is that that's that point right here where they run into each other. Okay. Over here where y equals 1, I'm going to have x squared is equal to 1 plus 2, meaning x squared equals 3, meaning x could equal the square root of 3, or maybe x could be the negative square root of 3. Okay, the solutions that will give me is x is the square root of 3, y is 1, or maybe x is the negative square root of 3 and y is 1. Now that's these 2 points. And you can see, even with my very poor drawing, that this figure does have a sort of symmetry to it. They're going to have that same y level, and they'll just be the opposites x, y's. And we're seeing that reflected in our actual solution. So that's good. All right, the last example I've got for y'all is one that is definitely set up for elimination, right? This one is just looking at me and saying, like, I need to be eliminated. So the reason that it's prime for elimination is this right here that I'm coloring in green, right? I see that 5y squared and I see negative 5y squared. I'm going to entirely eliminate the y variable, and then I'll be able to have it just in terms of x's and hopefully get myself a nice little solution. So what I'm going to do is I'm going to add these two equations together. I'll have 2x squared plus 1x squared is 3x squared. 5y squared minus 5y squared is 0. And 24 minus 12 is equal to 12. Okay. And then I'll say x squared is 12 divided by 3, which is 4. Meaning that x could either be 2 or maybe x could be negative 2. All right. So each of these will require me to figure out a y value or a couple of y values that will make this work. Okay, so what I'm going to do is I'm going to plug in x equals 2. Okay, so 4 is 2 squared minus 5y squared equals negative 12. So I'm going to subtract the 4, and negative 5y squared equals negative 16. Y squared is I'm going to divide by negative 5, so it's positive 16 divided by 5. And then I'll take the square root, and y will be equal to positive or negative square root of 16 divided by square root of 5. So that's going to be 4 over the square root of 5. Okay, so from x equals 2, I could have 2 and y is equal to 4 over the square root of 5. Or maybe I could have 2 and y would be negative 4 over the square root of 5. I'm going to plug in x equals negative 2 to that same equation. Okay, so I'll get negative 2 squared is 4 minus 5y squared equals negative 12. But if you look at it, that's the exact same equation as I had over here, so it's going to solve the exact same way. So I'm going to kind of, not do the same thing twice, not waste my own energy. So I'll say y is going to be equal to plus or minus 4 over the square root of 5 again. And so then the solutions that I'll have from that will be where x is negative 2. 4 over the square root of 5. And then negative 2 and negative 4 over the square root of 5. And so that's got 4 solutions. And I think that's about as complicated as we could possibly end up with with this type of thing. And I think I've covered all the different cases: substitution, elimination, no solution, how many solutions, the one that's definitely a common CLEP question. So from here, I would just encourage you to practice